Okay, in this question, we've got fluid with a viscosity. This is kinematic viscosity here. Notice this is a Greek letter nu, not the letter V. Okay, so it's viscosity. And also its density, 800 kilograms per meter cubed. And this fluid flows through a 8 centimeter diameter cast iron pipe from point 1 to 2 as shown in the diagram. We've got some additional information on the diagram. We've got the length between these two pressure tappings, and we know what the gauge pressures are of these pressure tappings, and also the change in elevation between the two. And we're told to estimate the mass flow rate for the conditions shown in this diagram. Okay, so first things first, if we write down Bernoulli's, so again we've got the static pressure plus dynamic pressure plus potential pressure. Point 1 is equal to the same thing at point 2 plus the pressure losses due to friction. Now, because this is a constant diameter pipe, the velocity at 1 is equal to the velocity at 2, assuming that it's incompressible. So it's got the same volumetric flow rate and there's no change in area, so therefore the velocities have to be the same. And we don't know what the height is at 1, but it doesn't matter because we're just looking at a change in height, so we're going to set 1 as our datum, so therefore Z1 is equal to 0. So that means these two terms will cancel, and also Z1 will cancel. Now, there's one other simplification that we can make. We need to remember that the pressures in Bernoulli's are absolute pressures, the static pressures. P1 and P2 are absolute pressure. But the absolute pressure is the gauge pressure plus atmospheric pressure. So if we rewrite P1 and P2 as P1 gauge plus atmosphere and P2 gauge plus atmosphere, then we can see that these atmospheric pressures, although we don't know what it is, they cancel out. So what we're left with is that the pressure loss along the pipe is equal to the difference in the gauge pressures minus the change in elevation. And we know what the two gauge pressures are, and we also know the change in elevation. Therefore we can see that the pressure loss is equal to 6,460 pascals. So this is a type 2 problem because we know the pressure loss between point 1 and point 2. We know the diameter, but we don't know the velocity. That's what we're trying to find out. And the type 2 problem is obviously a bit more tricky than type 1, because if we don't know the velocity, we can't find the Reynolds number, and if we can't find the Reynolds number, we can't find the friction factor. So how do we get around this? Well, if look back to the lecture, the way that we do this is we assume that the flow is fully turbulent. If you look at the Moody diagram, you'll see that for fully turbulent flow, the friction factor is independent of Reynolds number. It's only dependent on the relative pipe roughness. So we take advantage of that and say that for this type 2 problem, when we don't know what the velocity is and therefore can't work out the Reynolds number, we assume that it's fully turbulent, and it's a way we can get around that. And then we just need to iterate to our solution. So from the Moody diagram, from the question, we were told that it was a cast iron pipe. Therefore, we read off from the Moody diagram that the roughness is 0.15 millimeters, and that allows us to calculate the relative pipe roughness, because we were told that the diameter of the pipe was 8 centimeters or 80 millimeters. So that gives us relative pipe roughness. Now, I haven't showed you how to, I haven't gone through the step of reading it off the graph. I'm assuming you can do that by now. If you're not sure how to do that, look back at one of the other examples or the lecture. But you should get a friction factor of 0.023. So this is remembering this is a Darcy-Weisbach equation. So we know the pressure loss, we now have a friction factor, and we can calculate the velocity. So we rearrange to make velocity the subject and plug in the values. But remember this value, and if you do that, we work out the velocity to be 1.36 meters per second. But this isn't the answer. This is just our first guess, because we didn't know because we made an assumption that the flow was fully turbulent, we have to go around a couple more times. We have to take this new velocity to work out a new Reynolds number, to work out a new friction factor, to work out a new velocity, and keep going around until the velocity doesn't change much. Okay, so we take the velocity, 1.36 meters per second, that we got on the last slide, calculate a new Reynolds number. We now look this up on the Moody diagram using the relative pipe roughness, which doesn't change, and that gives us a new friction factor of 0.0245. We now then use this friction factor to calculate a new velocity using the same rearranged Darcy-Weisbach equation, and this gives us a new velocity of 1.32 meters per second. So our last value that we calculated, or the value of our first guess, was 1.36 meters per second. Our second guess is 1.32. So you can see it hasn't changed much. In fact, there's only a 3% change from the previous velocity. Therefore, there's no need to refine any further, and therefore we will take this as our final answer. Or it's good enough for the application that we've got here. Just remember that that's not the last part of the question. That's obviously quite an important part of the question, to find this velocity, but we were in fact asked to estimate the mass flow rate. So from this velocity, we then just need to work out the mass flow rate from density times area times velocity, and plug in all the numbers, and that gives us an answer of 5.32 kilograms per second.